shall not pass unless you loosen those follicles!
Continuing with the electric circuits topic, today we're going to be taking a look at electric fields. Your key learning for today is recall the shape of an electric field, apply knowledge of electric fields to infer how charges move, analyze experiments showing electric field properties, and hypothesize why we get sparks. Before we move on to the new information, let's see how much you can remember from the first lesson on this topic. I would like you to watch the video and answer the question that's been posed by Gandamp. Gandamp will prompt you to pause the video. At that point, pause the video, have a go at the question and try to include as much detail as possible. When you're ready to move on, Gandamp will explain the answer. Please mark your answer using Gandamp's explanation.
Here I have some pi cases. And if I was to turn on the Van de Graaff generator, what would happen to the pi cases? Pause the video now and have a think. When you're ready to move on and find out, press play. Okay, let's find out if you're right. So, we turn on the Van de Graaff generator. The Van de Graaff generator becomes positively charged in its dome. And as it becomes positively charged in its dome, we should see that the pi cases also become positively charged. And as like charges repel, all of those positively charged pi cases will repel away from each other.
Let's take a look at electric field shape. For your physics GCSE, you need to be able to draw the electric field pattern for an isolated charged sphere. I'm going to use this free spinning straw on the end of a meter rule to show you how that works. The straw will find the pattern of the electric field. Note that the pattern of the electric field is always radially outwards away from the charged dome. If we turn the rule on its side, we can also see that that is true towards the camera. This is because the field is three-dimensional, like this diagram here. But don't worry, that's not the one they want you to know how to draw. For your GCSEs, you need to be able to draw the two-dimensional version of that diagram, which looks like this. So you have a positive charge in the middle, and you have the lines of force, or the field lines, moving or pointing directly away from the charged sphere. Your diagram will look something like this. Note that for a positive charge, the arrows are pointing radially outwards, away from the centre of the charged sphere. However, if the sphere is negatively charged, the diagram looks almost the same, with one exception. The arrows are pointing towards the charged sphere. But what do the direction of the arrows mean? Well, think of it in this way. If we place a pair of positive charges close to them, it tells you which direction those charges will move. A positive and a positive will be repelled, so the charge will move outwards. But a positive charge near a negatively charged sphere will be attracted to that sphere. Remember, opposites attract. So, let's physically see this in action. What I am going to do is I'm going to induce charges, opposite charges, in these two spheres insulated from the ground by the means of induction. Now, you don't need to know how induction works, but if you are interested, then I will leave a link to an appropriate web page in the description. Now, all that I have to do is I have to hold a charged rod, charge my fun fly stick, hold that close to this side, and move that one away. Now what should happen is the one on the right hand side should now have a positive charge, and the one on the left hand side should have a negative charge. Next thing I'm going to do is I'm going to take something called a pith ball. Okay, just a little ball. At the moment it's not charged, but I'm going to touch it with the fun fly stick, which means it'll gain a positive charge. And let's start by holding it next to the negative sphere. Okay? Positive charge, negative sphere. You should see that it clearly attracted. Now that will have discharged the ball, so I'm going to recharge it again. So this time we're going to hold the positive test charge near the positive sphere, and we should see a repulsion. There we go. So it's refusing to go anywhere near that sphere. Now that you've watched the demonstration, let's have a look at testing your understanding of electric field shape. Have a go at the following. Number 1. Draw the electric field around a positive sphere and a negative sphere. Number 2. On your diagrams, insert a small positive charge and add an arrow to show the direction of motion in that field. Number 3. What difference would it make, if any, if instead of inserting a small positive charge for question 2, you inserted a small negative charge? And question 4, which is your challenge question, which is above and beyond what you need to know for your GCSE, why do you think we use a small charge to explore the electric field? Pause the video now, have a go at those questions. When you're ready to move on and find out the answers, press play. So let's take a look at the answer for question 1. Draw the electric field around a positive sphere. So starting with the positive sphere then, you should have drawn a diagram that looks something like this. A circle in the middle with a plus sign, with arrows coming radially outwards, pointing away from the center. For a negative sphere, you should have drawn something very similar, the only difference being that the arrows point inwards, towards the center, and you should have a minus sign in the circle in the middle. Question 2 told you on your diagrams insert a small positive charge and add an arrow to show the direction of motion in that field. So let's start with the positive sphere. If we add a small positive charge to that positive sphere, then the charge will repel away from the center of that sphere and it will move outwards. If you have a positive charge near the negative sphere, then it will be attracted towards that negative sphere and will move inwards. Note that the positive charge moves in the direction of the field lines. Question 3. What difference would it make, if any, if instead of inserting a small positive charge for question 2, you inserted a small negative charge? The charge would move in the opposite direction to a positive charge, which is in the opposite direction of the field. And question 4, your challenge question, which you do not need to remember for your GCSEs, is why do you think we use a small charge to explore the electric field? Well, if you use a large charge to explore the electric field, a large charge changes the shape of the field. We want to measure the field without disturbing it. Here are some examples of when we put large charges close to each other. So, for example, if we put a positive and a negative charge next to each other, it no longer appears that either of those charges are surrounded by that lovely radial field that you have been drawing in your previous questions. In addition to the shape of the field, you need to also know about the electric field strength. Watch the demonstration, make sure you pay attention, and we'll be assessing you afterwards. This is a plasma ball. It generates an electric field that extends beyond the glass. If you hold next to it a fluorescent bulb, you can clearly see that the electric field is strong enough to excite the atoms inside the bulb, making it glow. I'm interested in whether it makes a difference as to how close the bulb is to the ball. So as you bring the bulb in Can you see any difference? Does the field strength change depending on how close the bulb is to the plasma ball? Here I'm holding an LED. A little bit clearer to see. The LED also needs an electric field. The stronger the electric field, the brighter the LED. Can you see a pattern? If you're still not convinced, let's take a look at this using a meter. If you take a look at the dial, you can see that the electric field is strongest close to the charged object, and it becomes weaker the further away from the charged object you become. Now that you've seen the demonstration, let's take a look at some questions. To test your understanding of electric field strength, complete the following tasks. Number 1. Describe the relationship between the electric field strength and the distance from the charged sphere using your observations of what happened to the LED. Number 2. If instead of an LED we held a positively charged particle close to the plasma ball, where would it feel the strongest force? And number 3, which is your challenge question, looking back at your electric field line diagrams, what do you think the relationship is between the electric field strength and the distance between the electric field lines? Pause the video now, have a go at those questions. When you're ready to move on, press play. Let's check your answers. Question 1. Describe the relationship between the electric field strength and the distance from the charged sphere using your observations of what happened to the LED. Well, as the distance between an object and the sphere decreases, the electric field strength increases. This was seen by the LED getting brighter as it was closer to the plasma ball. Question 2. If instead of an LED we held a positively charged particle close to the plasma ball, where would it feel the strongest force? Well, as the force felt by a charged particle is related to the strength of the field, the highest force would be where the field is strongest, which would be close to the charged sphere. Question 3, which is your challenge question, looking back at your electric field line diagrams, what do you think the relationship is between electric field strength and the distance between the electric field lines? Well, let's take a look at our positive charge here. If you take a look close to the positive charge, the field lines are quite close together. Where the field lines are close together, the field is strongest. Further out, the field lines are further apart. So, the field gets weaker as the electric field lines get further apart. Back to the Van de Graaff generator. What would have happened if GaNDamp wasn't insulated from the floor using the plastic stab? Here you can see a series of discharges coming from the sphere into GaNDamp's hand. These are called sparks. Your job moving forward is to hypothesize how sparks form. Let's take a look at some larger sparks using the discharge sphere. What I would like you to do is I would like you to start to come up with your hypothesis as to how we get sparks. And this is how I want you to do it. I would like you to get a sheet of paper, and I would like you to write down the question at the top of that sheet of paper: why do we get sparks? You may already have an idea of how we get sparks from today's lesson. So, underneath the subtitle fields, write down your theory of how we get sparks. However, this won't be an adequate explanation as to how sparks are formed. In order to form a fully rounded explanation that involves all the necessary physics, you need to also understand some of the topics that we are going to be covering over the next few lessons. So, also write down subheadings for current, potential difference, and resistance. And over the next few lessons, I would like you to take some notes on how we get sparks using those ideas. Thanks for watching. That's the end of the lesson.